To introduce the second speaker of today, Professor Nakaoka. And Professor Nakaoka will speak about localization of extriangulated categories. Please.
Thank you very much for the introduction. I'd like to thank the organizers for allowing me to talk here. Today I will talk about the localization of extriangulated categories. This is a joint work with Yasuaki Ogawa and Arashi Sakai. So let me start with introduction. So extriangulated category, which I call ET category for short in this talk, can be regarded as a common generalization of exact categories and triangulated categories. So it fits here. It is defined as an additive category equipped with some extra structure. One of the advantages to use ET category is that this class is closed by some basic operations, such as taking extension closed subcategories, ideal quotients, and relative theories. But we know another basic operation for additive categories, namely localization. So how about localizations for ET categories? So ET category contains exact categories, abelian categories, and triangulated categories as special cases. For such categories, we know several localizations. For example, we know the Verdi quotient of triangulated categories, and similarly, cell quotients of abelian categories. Well, cell quotients are generalized to exact categories, with the localization of exact category by percolating subcategories by recent work of Henrik van Roosmalen. There is also another localization by resolving subcategories given by Rump. This localization gives triangulate category out of exact category. Also, there is some localization for ET categories via something which we call Hove twin quotation pairs. This construction unifies some known localizations via nice model structures. Abelian model structure is introduced by Hove. The exact case was by Gillespie, and triangulated analog was by Yang. How you hope to unify all of these localizations. And before stating our main theorem on the localization, let me briefly review the basics of ET categories. The notion of ET category was introduced in a collaboration with Jan Paru. It is defined as a triplet of an additive category C by additive functor E from C of times C to the category of small abelian groups. Something which we call realization of E. So what is the realization? Well, it is a correspondence which associates to any element delta of E of CA to some sequence. Well, we call such an element delta an extension. So this realization S sends delta to some sequence. More precisely, it is an equivalence class of two-term sequences starting from A and ending in C. Here, the equivalence relation is given like this, namely, two sequences xy and x prime y prime are equivalent if there is some isomorphism in the middle. We denote its equivalence class by taking brackets like this. Well, and the required conditions can be described in terms of X triangles. An X triangle is a pair of extension delta and a sequence in which the realization S sends delta to the equivalence class of this sequence. Well, we denote the X triangle in this way. Here is delta, and the sequence is here. In such an X triangle, the morphism X in the left is called inflation, and the morphism Y on the right is called deflation, just as in the case of an exact category. And the sequence appearing here is called a conflation. So it is an X triangle is a pair of extension and conflation. And also we call object C here the cone of X. It is determined by up to isomorphism from X. And dually, object A here is called the cocone of Y. And before the detail of the conditions, let me introduce the category of extensions. So the category of extensions is studied in detail, for example, in a recent paper by Bennett-Tenenhaus, Haugland, Sandoy, and Shao. In the category of extensions, objects are extensions, namely delta in E of CA for some pair of objects C and A in the category C. The morphism from delta to delta prime is sometimes depicted like this. So here, delta is an extension, and delta prime is also an extension. So these are the objects. And the morphism from delta to delta prime is a pair of morphisms in the category C. So A and C are morphisms in C. And this should satisfy this equality. Let me explain about this equality. Since E is a functor from C of times C, we can push delta by morphism A, and also pull delta prime by morphism C. So this equality is saying that delta pushed by A is equal to delta prime pulled by C. So it's something like the commutativity of this square. And we often abbreviate this A push delta in this way, namely A push delta. And also the right-hand side is abbreviated to C pull delta prime. So this equality is often written like this. Well, more briefly, in this way, A delta is delta prime C. Yep. So this is the category of extensions. On the other hand, in the category of X triangles, well, objects are X triangles, and morphism between them is a triplet of morphisms in C, depicted like this. So this triplet should satisfy the three compatibilities. The first one is the commutativity of the left square. And the second one is the commutativity of the right square. And the remaining third one is the the compatibility A delta equals to delta prime C. So it is saying that the pair A, C is a morphism from delta to delta prime in the category of extensions. Yes. So this is a category of X triangles. Now let me explain the conditions for ET categories in terms of X triangles. There are three conditions. The first one is the additivity of the realization. So it requires that if we are given two X triangles, then each term-wise direct sum becomes again an X triangle. So we take direct sums term by term, then it becomes an X triangle again. Here delta plus delta prime is the direct sum of two extensions in the category of extensions. So this is the first condition. The second condition allows us to obtain morphism of X triangles. So a morphism of X triangles is, by definition, a triplet A, B, C of morphism is in C, like this. And if we lack one of these three, we can complete it into a morphism. Well, this condition corresponds to tier 3 for triangulated categories. But because we cannot rotate X triangles, we have to consider three cases. More precisely, if we lack C, namely if A and B makes the left square commutative, then there exists some C which forms a morphism of X triangles. And also, if B and C makes the right square commutative, then we can find some A to form a morphism of X triangles. And lastly, if we are given a pair AC, which is a morphism of extensions, then there is some morphism B in the middle, which form a morphism of X triangles. And as in the case of triangulated categories, these complements are not unique nor functorial, so there doesn't exist any canonical choice. Yep. So this is the second condition. And the last condition is an analog of the octahedron axiom. If we are given two X triangles in this way, then we can complete it into an octahedron of this form. Well, this is in particular saying that inflations are closed by compositions. Namely, in the given X triangles, F and G are inflations. Then in the completed octahedron, the composition of G and F is again an inflation. So inflations are closed by compositions. And again, since we cannot rotate X triangles, we also assume it's dual. And by duality, deflations are also closed by compositions. So this is all of the conditions in the definition of an ET category. Oh, the two typical examples of ET categories are exact categories and triangulated categories. The first example is an exact category. Suppose that suppose that C, S is an exact category. Here S denotes the conflations for exact category, namely a given class of kernel-co-kernel pairs satisfying some conditions. So starting from an exact category, for any pair AC, for any pair of objects AC in the category C, we can define X1 group X1C of A in this way. So it is a set of equivalence classes of conflations starting from A and ending in C. And the equivalence relation is the same as before, the same relation as before. Yeah. And if these X1 groups are small, it becomes a bi-additive functor to the category of small abelian groups. So let us require that these X1 groups are small. Then we have functor X1. So this is our E. And now we have to give a realization. Remark that any element, namely an extension delta for this bi-additive functor is of this form. Namely, it is nothing but an equivalence class of sequences. Hence, as a realization, we can take an obvious correspondence identity which sends delta to delta itself. So in this way, we can regard an exact category as an ET category. We remark that in this case, X triangles are essentially the same as conflations, and with the information of delta in an X triangle is somewhat redundant. The other example is a triangulated category. So suppose C is a triangulated category. Then we can define a bi-additive functor by considering morphisms shifted by 1. Namely, an extension for this bi-additive functor is nothing but a morphism from C to A1 for each pair of objects in C. And now let us give its realization. For each such morphism, we can complete it into a distinct triangle of this form. And then we define S of delta to the equivalence class of the sequences appearing here. In other words, we can say that we defined X triangles to be distinguished triangles. And in this way, any triangulated category can be regarded as an ET category. Well, let me skip a bit. Yep. So exact categories and triangulated categories are typical examples of ET categories. And conversely, we can characterize among ET categories which are exact categories and which are triangulated categories by very simple conditions. So let's see be an ET category. Well, this proposition 1 says that this ET category becomes an exact category if and only if any inflation is monomorphic and any deflation is epimorphic. Now, the next proposition 2 says that, well, maybe I wrote too much, but the second one is saying that C is naturally a triangulated category, and it is equivalent to the first condition, namely any morphism in C is both inflation and deflation. So this condition characterize which ET categories are triangulated categories. And now let me move to our main part. For the settings, firstly, let's see be an ET category, which I assume to be small from now on. Now we want to localize C, so let S be a class of morphisms in C. So it is a class of morphisms to be invalid. To such S, we associate a full subcategory NS of C in this way. Well, this is saying that the object N here is something which should become 0 after the localization. Now starting from C, we take the ideal quotient by this NS. So we are killing the ideal consisting of morphisms which factor through some object in N. And then send the class S by this functor P to obtain S bar in C bar. And by using S bar, we localize C bar to obtain C tilde and denote the composition of these two functors by Q. So this Q is a localization factor if we invert the class S. Now the problem is to find a condition for S under which the resulting C tilde has a natural or universal ET structure. Our main theorem gives such a sort of conditions. Well, I do not explain the detail of these conditions, but MR1 and 2 are to make the calculation of morphisms in the localization easier. And the third condition, MR3, is claiming that S is compatible with the ET structure on C. And the last condition, MR4, is required so as to ensure that the inflations and deflations in the localization are closed by compositions. With these conditions, C tilde has a natural ET structure, which is universal in some sense. Well, instead of explaining the detail of these conditions, let me briefly sketch how to give ET structure on the localization C tilde to show that the construction is somewhat natural. Firstly, by MR1 and 2, we may calculate morphisms in C tilde easily by using roofs in C bar. So any morphism in C tilde can be expressed as a roof in C bar. It is a pair of F bar and S bar, in which S bar belongs to this S bar. And then we define E tilde by localizing the original functor E both from left and right by S bar. More precisely, we define E tilde of CA to be the set of equivalence classes of this type of triplet In the middle, delta is an extension in the original E, and S bar on the right and T bar on the left are morphisms in S bar. So we denote an element in E tilde of CA in this way. It is an equivalence class of this sequence. And now we want to associate an X triangle to such an element T bar delta S bar. Well, since C is an ET category, we have an X triangle in C associated to the delta in the middle. So this is an X triangle in the original ET category. And then simply by composing S bar and T bar, we can define X triangle in C tilde. So this is a definition of ET structure on the localization C tilde. In the remaining time, let's see how we can recover the known localizations. Let us introduce the notion of a sixth subcategory. Well, subcategory is assumed to be full additive and closed by isomorphisms. Such a subcategory is called thick if it is moreover closed by taking direct summands and satisfies 2 out of 3 conditions for conflations. Namely, in any conflation like this, if 2 of A, B, C belong to N, then so does the third. And for a sixth subcategory N, we associate the following classes of morphisms L and R. L consists of inflations whose cone is in N, and R consists of morphisms which are deflations whose co-cones are in N. So these morphisms should become isomorphism, we hope. Yeah. And then we take finite compositions of these morphisms to obtain a class of morphisms S. Yeah. And let me remark that if C is triangulated, then Sn agrees with both L and R. And now we want to apply our theorem to this Sn. So the question is that when this Sn satisfies the assumption of the theorem. And as our answer, it is fulfilled in each of the following 2 cases. Case A is that N is a bi-resolving subcategory. A sixth subcategory N is called bi-resolving if any object C admits a deflation from some object N in N, and also an inflation to some object N prime in N. Now, if C is triangulated, this condition is always satisfied by any sixth subcategory, because any morphism is inflation and deflation. The other case B is that N is a percolating subcategory with unfortunately some technical conditions. It is called a percolating subcategory if any morphism which belongs to the ideal N should admit a factorization in this way, namely it is a factorization into deflation to some object N in the category N, followed by an inflation. And if C is an exact category, then this agrees with the original definition by Henrad van Roosmalen. And the technical conditions here are always satisfied. For case A, suppose that N is a bi-resolving six subcategory. In this case, morphisms in Sn can be written as a composition of R and N in this direction. And we can show that Sn satisfies the assumption of the theorem. Moreover, morphisms in Sn bar are ones which are both apomorphic and monomorphic in the ideal quotient C bar. And by the theorem, C2 becomes an ET category. But in this case, moreover, it becomes always triangulated. Now, this case recovers the following examples. So if C is triangulated, then this is nothing but the Verdi quotient. And if C is exact, then this recovers Rump's localization. And lastly, if C is weakly idempotent complete ET category, equipped with a Hove twin quotation pair, then we can associate some by resolving six subcategory. And by the theorem, the resulting localization is triangulated, which was also shown in the earlier collaboration with Yang. For case B, suppose that N is a percolating six subcategory satisfying the technical conditions. Well, in this case, morphisms in Sn can be written as a composition of morphisms in L and R in this direction. So it is in opposite direction compared to the case of bi-resolving subcategories. And we can show that Sn satisfies the assumption of the theorem. And by the theorem, C2 becomes an ET category. And in this case, the resulting category tends to become an exact category. For example, if C is exact, then it automatically becomes exact without any additional condition. In this case, B recovers the following examples. So if C is exact, then this localization recovers the localization given in Henrad van Roosmalen. So in particular, if C is Abel, it is nothing but a cell quotient. I'm sorry, it's too fast. Sorry, that's all. Thank you very much.
Thank you very much for your nice talk.
Thank you.
Are there any questions, comments?
Hi, thank you for the nice talk. I would like to ask, I'm a little bit confused about the first step of the localization. You have to go to the ideal quotient, and maybe you can give us an example in the case of triangulated categories. What is going on with this ideal, with the first step?
Yeah, I'm sorry. If C is triangulated, probably we don't have to take ideal quotient. Yeah, I'm sorry.
In this case, you go directly to the quotient, the next step. Am I right?
Yeah.
Okay, thank you.
Yeah, sorry.
Thank you.
May I ask a question? Also about an example. For example, let's take the category of complexes over an abelian category. Yes, say with the component-wise split exact structure, and we want to localize with respect to quasi-isomorphisms. Would this be would this fit into the picture? And in this case, in the first step, would you take the ideal quotient by all acyclic complexes?
Let me see. Yeah, so C is exact category in that case. Yeah.
Mm-hmm.
Maybe it's. I hope it becomes some homospeed category here, but why? So the resulting localization is the derived category, and
Yes.
I hope this is a homotopy category.
Uh-huh. But NS would be the subcategory of all acyclic complexes in that case. If I'm not mistaken.
Yes. Yes.
I mean, maybe that's also a good category, but it would be a quotient already of the homotopy category. Mm-hmm.
Sorry, I'm not sure.
Yeah, of course, there is no contradiction. Only the category C bar is a bit unexpected.
Hmm. Mm.
Well, it's not an important question.
No,
Thank you
sorry.
thank you very much for the talk in any case.
Maybe if you localize by causal isomorphism, the category complexes with the that exact structure, maybe in the resulting localization, maybe X triangles are a bit lesser than the derived category, maybe because we are taking relative theory in C. So it might be the case that not all triangles come from the X triangle from C.
Yes. No, I think that's okay. I mean, yes.
Yeah, I'm sorry, I can't answer clearly. Sorry.
No problem. Thank you very much for the talk.
Thank you very much.
Are there any questions or comments? Not. So thank you again for your nice talk.
Thank you very much.